Okay, well, firstly, thank you to the Howard Foundation and to Alan for organising today and for the invitation. I'm Mike Lockwood. I'm a solar physicist and a solar terrestrial physicist. And so I would really love to be able to stand up here today and say global climate change is all about changes in the sun. It would make my H-index go through the roof. Academics worry about our H-index, which tells us who is looking at our papers. And I'd also be delighted because found out just a few weeks ago that I'm about to become a granddad. And I think the stewardship of this planet and the lifestyle of the people on our planet will be an awful lot easier were I able to stand up and say that. So I would love to. But what I want and what I would like to be able to say is utterly, utterly irrelevant. I'm afraid science doesn't care what anybody wants. Science just is, and our job is to find out what is. What I'm going to do in this talk is I want to look a little bit at solar outputs that at some stage have been suggested as causal agents of climate change on our planet. I then want to look at what we know, because we've learned quite a lot in recent years about how the sun has varied on long-term, by that I mean century timescales. I'll then look at the global effects of that before moving on to a rather more local European and UK regional and seasonal effect that we think may be there, and then look into the future a little bit in terms of the future of what the sun is likely to do. So let's start with looking at the solar outputs. They all relate around something you can see in this marvelous eclipse picture. You can see these striations here in the solar atmosphere. This is when the moon has blocked out the light from the photosphere. Those of you with good eyes will actually be able to see features on the moon, which is the ashen light. It's the earthshine illuminating the dark side of the moon. Those striations in the solar atmosphere are caused by the presence of magnetic field. And it's magnetic field that causes all the things that we might be interested in. You can actually put some kind of sketch of what the magnetic field at sunspot minimum would look like. It's something like that at this time. And where that field threads the solar surface, that produces the most well-known manifestation of solar magnetism, sunspots. But it also modulates, through sunspots and actually smaller features called faculae, it modulates the total solar irradiance, the brightness of the sun, which of course powers our climate system. A bit higher up, at the very base of the solar atmosphere, the so-called chromosphere, the magnetic field modulates the ultraviolet that the sun gives off. And I'll talk a bit more about that. Further up into the atmosphere, it modulates, it almost completely controls the extreme ultraviolet and the X-rays emitted by the sun. And then further, if we take this field, goes all the way out, it surrounds all the planets, we call it the heliosphere, and that field and actually structure in that field produces what is effectively another solar output, and that is the number of cosmic rays which are produced in supernovae explosions, but we are protected from them by the magnetic field. So as solar activity goes up, the number of cosmic rays reaching us goes down. So it's effectively a solar output as far as we're concerned. Okay, so let's take a look at those. The modulation of the surface magnetic fields of the total solar irradiance, dominated by the visible and infrared, is incredibly small. It's a very weak variation. On decadal timescales, we're talking about 0.1%, so a very weak modulation indeed. The ultraviolet is modulated rather more, by which I mean about 1%. This is half range to average value. The ultraviolet is the extreme ultraviolet coming from higher in the solar atmosphere is highly dependent on the magnetic field. It's about a 50% modulation. And the X-rays are almost 90% dependent on that magnetic field. This actually, by the way, is an image of the sun seen in those different wavelengths. The very high temperatures at the shorter wavelengths that it's moving to now, the last plot will be the X-ray sun. They actually drive another output of the sun, the solar wind. This is thermal plasma, temperature about 1/10 of a million degrees, and it's about 65% modulated over the solar magnetic cycle. The cosmic rays depends on the energy of cosmic ray you're talking about, but something like 20 to 40% modulation depending on the energy. And lastly, there are things called SEPs. In the Hitchhiker's Guide, they stood for someone else's problem. They are, in a way, they're astronauts' problems. They're not nice if you're in space. They're about 100% modulated by magnetic field structures in the interplanetary medium and a little bit by flares on the solar surface. So what do they do when they reach our atmosphere? Okay, well, first of all, we have to have a look at the height profile of the atmosphere, shown here by the temperature profile. All our weather and climate is down here in the troposphere. If we look at where the various electromagnetic radiations come, the visible and infrared reach right through to the surface. We know that, particularly on a nice day like today. The ultraviolet largely is stopped in the stratosphere by the production of ozone. Ultraviolet produces ozone, but then is absorbed by it. So the ultraviolet strongly heats the stratosphere, and it's the reason why the temperature profile goes back up again. The extreme ultraviolet only really affects the very top of the atmosphere, the so-called thermosphere. The X-rays reach a little bit lower down, but still only affect the thermosphere. Now, I want you to just notice the numbers down the side here. This is the density. So if we have 1 here at the surface, it's a millionth of that up in even the lowest part of the thermosphere. So there's 1 particle for every million at the surface. This is an incredibly sparse gas up here. And there really are no credible mechanisms for transferring any of the variability undoubtedly introduced by these wavelengths down into the troposphere. What about the particles? The SEPs, actually, they do reach down. They have a catalytic destruction of ozone, and that may have effects in the stratosphere. The cosmic rays don't actually reach the surface, but their products, like neutrons, do, and we can observe them from the surface, but they do reach right down into the troposphere. And the solar wind only affects the thermosphere again. So if we take a look at the possible effects, the visible infrared, well, there have been detections of the solar cycle variation in tropospheric temperatures and surface temperatures, so what we would call bottom-up effects, because we're heating the surface and it's going up into the atmosphere. They're extremely small, and they're very debatable, because there are lots of other things, like ocean oscillations on decadal timescales, that you can very easily confuse. So the evidence is far from straightforward on that, but they have been talked about. The ultraviolet is different. There are clear effects of the ultraviolet in the stratosphere, heating and wind effects in the stratosphere. And there is interest in rather subtle top-down effects. The stratosphere is still a very, very sparse gas compared to where our climate is, and people talk about the tail wagging the dog, but there may well be subtle effects from the stratosphere down, and I'll talk a little bit about a possibility of that, but it's far from proven yet. Again, EUV dominates the thermosphere, so does the X-rays, so does the solar wind, the cosmic rays. I'm not going to talk much about this because you'll hear about this in the next talk from Henrik, but it's just been proposed that cosmic rays can modulate cloud, help the formation of cloud. I should say, and the effects of that depend critically on the height of the cloud that you're talking about. Does that trap in more than it reflects solar shortwave, or etc.? Henrik will talk about that. I should nail my colours to the mast on this. I actually think it's a lovely idea. And I do think it happens. I think it happens, but very, very slowly. And that means that it's only really relevant in very clean maritime air, where there's a real shortage of other things for clouds to condense on. Normally over land, in particular, you have enough aerosols that clouds will condense very readily. But I've been working with Giles Harrison at Reading, and we do think we have some evidence for a slow effect in clean maritime air. But it's a lovely idea. It's a really very clever idea. The question is, does it matter on long timescales? And that's something I will address in my talk. And then, as I've already mentioned, SEPs destroy ozone, and so they may have effects similar to ultraviolet. So I'm going to get rid of those that are affecting the thermosphere, because the thermosphere is such a sparse gas. There really is no credible observations or mechanism for transferring that energy down to where our climate is. And we're left with these guys. I'm going to get rid of SEPs, because we have no evidence for long-term change in the rate of SEPs. And also, at solar minimum, they go away anyway, so there's nothing to take away. So if we go back in time, we can't remove any, because there aren't any to remove it. So let's take a look at what long-term variability we have in the other parameters. Now, this shows you the variations of some things that we know about the sun back to over 150 or so years. And I've taken the plot deliberately up to 1985. It's the smooth plots. It's the solar cycle averages of all the parameters. So this is the sunspot number, and it rose over the last century. It wiggled around a bit after that. This is the magnetic field leaving the sun. I derived it first from geomagnetic observations about a decade ago. Got a lot of flack for doing so, but a decade on, everybody now seems to just about agree with it. And so, again, it looks very like the sunspot number. So this is the magnetic field of the sun. This is an interesting plot. It's the cosmic ray flux. Now, this has come from Friedhelm Steenhilber in Switzerland. Back here, it's based on beryllium-10 isotope, which is produced by cosmic rays and stored in reservoirs like ice sheets. Up here, it's based on the climax data, and in fact, the whole thing's been scaled in terms of the climax neutron monitor counts. Actually, putting those two together is not a simple task. Friedhelm used a model of beryllium-10 production and deposition so that he actually knew how his ice core related to the global means and things like that. It's not an easy thing to do. This is a reconstruction of the total solar irradiance. It's based on this magnetic field and the sunspot numbers, essentially. A key point is how small the drift is. Again, it's about the same as the solar cycle amplitude, 0.1%. In terms of radiative forcing, that's a change between here and the modern day of about 3/4 of a watt per square meter. To put that in context, to understand the observed temperature rise, you need something like 5 watts per square meter. Okay? And it's much smaller than the projected rise because of greenhouse gases, trace greenhouse gases. And then lastly, we have the data that Phil showed you this morning. This is the Hagkrutt 3V, global mean surface temperature, air surface temperature, and the rise over the same period. Now, all right, there are some wiggles, but the essential feature is all the solar activity indices that have gone up have gone up. Cosmic rays go down because they're anti-correlated. This is the solar cycle length, which has also gone down. It's well known to be anti-correlated with solar activity, and temperatures have risen. So although you can't match up individual bumps and things like that, overall you could say, well, solar activity could have contributed to the temperature rise. But then we have to have a look at what's happened since 1985. The sunspot number has fallen, and the recent very low solar minimum is just part of that progression. The length of the cycles have increased. The magnetic field of the sun, this is based on satellite data instead of geomagnetic activity data now, that has fallen. The cosmic ray flux has recovered. The irradiance has fallen, and yet the temperatures have continued to march upwards. Okay? And so if we put the two together, put it in context, it's really rather interesting to look, for example, at the cosmic ray variation in that it did fall. So this means that there was a decrease in cosmic rays, and Henrik will tell you what he thinks that does to our radiative balance on the Earth. And it may possibly have been associated with this part of the rise. It could have contributed. However, since then, it's been relatively flat, and at the moment, it is recovering, and yet temperatures have continued to accelerate upwards. So the changes in the sun, particularly over the last 20 or 30 years, just are in the wrong direction to actually explain what's been going on. So let's have a look at global effects. This is my view. A lot of these things were sort of said in various ways in the first session this morning. The sun undoubtedly powers our climate system. There are inputs that are man-made. There are inputs from volcanoes into our climate system. There are feedback loops. Clouds is a particularly poorly understood example. Clouds have two effects. They're very good water droplets, are good greenhouse trappers. So they add to the greenhouse effect, and they also are white. They reflect. They increase Earth's albedo. They reflect the solar shortwave back into space. And which they do is dominated by their height. So the dominant effect of those two opposing effects, one a cooling effect, one a warming effect, depends on the height of the cloud. We've heard about how the biosphere feeds back in, both through absorbing greenhouse gases and actually through change of surface albedo. We can have other factors like we melt the permafrost, it releases methane, which is a very good greenhouse gas. We melt the cryosphere, we change the albedo, we got feedback loops. We might have feedback loops through sea level change. We might affect ocean circulations. The oceans have a trick that Andy talked about, that their temperature determines their uptake rate, and so it can feed back into the greenhouse warming. So there's lots of feedback loops in there. And then the oceans have another trick of their own, which is we're interested in the surface temperature. We live on the surface, so it's the air surface temperature we're interested in. But the deep oceans can have an effect, and the dominant one appears to be El Nino, where warm water comes up in the Central Pacific in the El Nino events, and La Nina during cold. I think we should change those names, by the way. I don't think they're politically correct. El Nino is the boy, La Nina is the girl. So, sorry, they got to go. Okay, so we look at the various inputs, volcanoes. These are two stratospheric climate-effective volcanoes that have happened in recent years. Through atmospheric optical depth, we can watch the effect of that stuff girdling the Earth and then spreading out over the whole planet over about a 9-month period, reducing the amount of shortwave reaching the surface. We've heard about man-made effects this morning. The sun, if it changes because it powers our climate system, it clearly could be a factor. And then El Nino. Now we can treat that all as inputs into the system. So how do we quantify them? Well, the El Nino is best quantified by the temperature in the middle of the El Nino region. This is the so-called N3.4 index. So these peaks here are El Nino events. The dips are La Ninas. This is the atmospheric optical depth. And you can see the major climate-effective volcanoes. This, I think, is Agung in New Zealand, El Chicho and Pinatubo. I'm going to use cosmic rays directly to quantify the solar effect. So this is the cosmic rays from Climax. Unfortunately, they stopped monitoring about here, so we've had to extend using a basket of other stations that are extremely well intercorrelated. But notice how high the cosmic ray flux reached during the recent solar minimum because of the low solar activity. And then this is the combination of man-made forcings predicted by the GISS. It's the Model E GISS input. It's a combination of greenhouse gases, aerosols, and land use change. Okay? So now we can put these together, and this is a multivariate fit. So you have to fit the amplitude of each of those, and you have to fit a time response, time constant, to allow for the fact that there might be a bit of a delay before it's implemented, but that time was allowed to vary freely. And you can see you can explain the observed temperature rise extraordinarily well with just these 4 simple factors. But I want to put a health warning on this. Interpret it with extreme caution, because this kind of multivariate fit is open to all sorts of errors. Firstly, I chose what input parameters to go in. I have a lot of free variables. There may be correlations between the input variables. You can overfit the data, okay? So this is not a detection attribution. However, it is a nice, simple demonstration that it's very easy to understand the temperature rise in terms of El Nino, greenhouse gases, solar change, and volcanoes. Okay? And this is the fit residuals, and there's no drift. There's a lot of noise, but we've got a nice lack of drift. So we've explained the long-term trends very well. So the advantage of this is we can take this and say, okay, what are the contributions? So these all are on the same scale. This is the contribution to that temperature change of the El Nino effect. You can see the El Ninos and the La Ninas. This is the volcanoes. It looks a little bit different because we've run it through a smoothing filter to allow for response time. This is the solar, and this is the basket of anthropogenic effects. Okay? No models used, just simple looking at the data. Okay? And what are the contributions to the total temperature change? If that's the total observed, then the solar is actually downward. As I said, the solar changes. This is based on using cosmic rays, but I can use irradiance to get the same answer. El Nino, there's actually been a surfeit of La Ninas compared to El Ninos in recent years. There's been a lack of volcanoes, and the vast majority is explained by the combination of anthropogenic effects. Now, one reason I wanted to look at this, well, firstly to say, well, could the fits have been confused? Let's say this is my best fit. If it's overestimated the contribution of the anthropogenic, on this plot, which is the anthropogenic sensitivity factor against the cosmic ray one, the solar one, then if solar could replace it, then this best fit would migrate in this direction. Is that possible? Actually, no. This shows you the difference in fit residuals. As we come away from the best fit here, the fit residuals get larger. This point here is the 2 sigma level. I am 95% certain that the best fit is somewhere in that circle. Okay? So no, there's no possibility of that. In fact, if I look at the correlation between the time series, I get this plot, which allows even less reduction in the anthropogenic effect. And I can look at the significance levels of that. And if anything, instead of going back that way, it's going that way. So in other words, if I turn up the solar effect, I've also got to turn up the man-made effect to compensate. OK, so that's on the global basis. But you can do the same analysis, and Phil was talking about this. I'm one of those people that wanted regional data. I want to know the maps. Now, I have done this with as well, but I was beaten to publication by Judith Lean by a matter of months. I was so annoyed when I read her paper. But that's academic life for you. What she did was she did that kind of analysis on every point of the globe. And so, for example, this is the response to El Nino, and it's dominated, it's very, very strong in the Central Pacific, as you would expect. That's where the warm or cold water is coming up. But it does have effects in other parts of the globe, particularly here in America. This was the response to a major volcano. This is the anthropogenic response, dominated by the Northern Hemisphere, as most of the models predict. But this is not models, it's just data. It's just multivariate fitting of the data. What I want to concentrate on is this peculiar dependence on the solar in the Eurasian region. Okay? I'd really love to have had enough data to look at it over Greenland, but there's a paucity of data, and instead of using extrapolated data, we just said we really don't know what's going on over Greenland. It would have been a significant test of what I'm going to say about this solar dependence. There's a hint, it's underneath the northern jet stream. There's a hint of the same thing happening, but to a much smaller degree in the southern hemisphere. Good, perfect. We became interested in these sort of events. These are events in the jet stream called blocking events. What they really are is just meanders in the jet stream. So you can see it here meandering back down. Instead of just heading off towards the east, it meanders back southwest for a bit and then round to the east. What that does, this is the temperature on the dynamical tropopause that the jet stream sits between the stratosphere and the troposphere. You see these low temperatures from the Arctic being dragged down over Europe. Okay? And in fact, because what you've got here is a large anticyclonic system, you have clear skies causing further cooling over eastern Russia here, western Russia, and that further reduces the temperatures. So in winter, these blocking events are a good way of reducing the temperature in Europe. And I should say that we find that most of that solar dependence on temperatures in Europe comes in winter. We had a very good example of what blocking can do about a year ago. I was very worried about getting to Vienna at the time, I remember. This was the unpronounceable Icelandic volcano eruption. It started heading off the plume in the direction of the jet stream, but it got caught up in a blocking event. And you get a very graphic demonstration of how a blocking event pulls air down from the north. In winter, that's cold air from the north and from the east. And in fact, going back in history, in the Maunder Minimum, people talked about cold winters. They mentioned they were always accompanied by cold winds from the east. So we looked at whether this could have a solar dependence. What we've done here is we've looked at the occurrence of those blocking events based on the, don't worry where we get the blocking index from. Essentially, this was high solar conditions minus average solar conditions, and we find about an 8% decrease in blocking when solar activity is high. The grey areas are where we are 95% confident from a Monte Carlo test that this is a significant result. This shows you the low solar activity against the average, and actually we've got an 8% increase in blocking, and again, it's 95% significant. We can't find anything equivalent in the southern hemisphere, and it's the only place around the northern hemisphere jet stream it happens. There is something special about Europe, we think. Looking at the temperatures, this is based on data from 1976 onwards. We find that these blocking events do duly reduce the temperatures, particularly here in Eastern Europe. But notice what it's done to Greenland. Okay, this is data. This is just sorting low solar activity minus high solar activity. It increases the temperatures over Greenland. This is not a global effect. It's just a redistribution of what's going on around the Atlantic basin. So you have to be very, very careful about taking regional climate data and extrapolating it onto a global basis. Regional climate and global climate are completely different things very often. And so you can find solar signals in certain places. It doesn't tell you about global climate change. It's something you've got to be very, very careful of. It also means your personal experience of climate change here in the UK may not be as relevant to the whole globe as you think. Taking a look at, these are height versus latitude plots. This shows you the correlation in the equatorial stratosphere with three solar indices. F10.7 is like sunspot number, cosmic rays, and open magnetic flux. In fact, open magnetic flux performs best. Correlation is highest and most significant here. So we know about that. That's the effect on the stratosphere. What's interesting, these are the zonal averages of zonal winds, and particularly here in the northern hemisphere again, at mid-latitudes, we're getting a solar signal cropping up, but only there. It's not global, it's local to us. We're in a strange position, and it even reflects in the surface temperatures, particularly when used the magnetic field of the sun to sort the data. So what we think is going on, or could be going on, is that solar ultraviolet is affecting the stratosphere, that actually existing planetary waves in the troposphere, driven by the high energy densities of the troposphere, but propagating upward, they hit the stratosphere, and what is refracted back down could be changed. And it seems that low solar activity allows more of these meanders to form, and so introduce blocking events. Let me just finish with a look at the future, because the sun is not like our climate system. We have no predictive models at all that work. We don't even have a three-dimensional model of the solar dynamo. But so we have to look back in time. This is that Steenhilber record I mentioned, going back over 9,300 years. And this shows you the solar variability. We are now coming to the end of what is the most long-lived grand solar maximum in that record. So it's overdue to end. What we can do is we can look at the end of all the grand solar maxima. By the way, this is the Maunder minimum here. Okay, so it's not a particularly deep or long-lived minimum compared to some of the others. And we can take a look at we can composite what went on around those. So here's our approach to the present end of the grand solar maximum. And this is what has happened in the 24 times it happened before in the past 9,300 years. And in 2 of the cases, we fall below this dashed line, which is the Maunder minimum level. So in 2 out of 24, it's about an 8% chance that within 40 years from now, we actually have Maunder minimum conditions, which will really test our understanding of solar variability. It may be that we don't get such a big dip. There are examples where it didn't fall so much, but it will fall. And so solar activity is due to fall. Let me sum up. Okay. So there is no evidence that stands up to really serious scrutiny that the sun has contributed to recent, the word recent is relative, I mean by at least the last 20, 30 years by that, global climate change. It may well have contributed before about 1930, but since then it's been kind of flat, and it's even been in the wrong direction for the last 30 years. Regional changes are quite a different thing from global changes, and so regional signatures do not tell you about global climate change. There is some evidence that Europe suffers more blocking and, as a result, cold winters when solar activity is low. And we think a promising explanation is this UV modulation of the stratosphere and the effect on our propagating tropospheric eddies. Let me just finish by saying science doesn't care about what I want. It doesn't care about what you want. It's immune to spin. You cannot spin away a scientific fact. It is a fact. Okay? The other thing that is true of it, though, is it does have a sense of irony, because we might have the irony that in a warming world, we in Europe might actually face more cold winters because of the solar effect. Okay, with that I'll finish.
First of all, thank you very much for inviting me and giving me the opportunity to present the work that we have been doing, a lot of it actually in Copenhagen over a number of years. My outline for the talk, it is cosmic rays, and I will talk about clouds because I think there is a connection between changes in cosmic rays and changes in clouds, and of course also on climate. So I will start by saying a little bit about cosmic rays. Fortunately, we already heard a little bit about it. I will say some few definitions about what cosmic rays are. Then I will present just a little bit of the empirical evidence that show that each time you have a change in cosmic rays, apparently you have a change in climate. And that means that there's a scientific question that needs to be understood. And this is the kind of question that we have been working on for a long time. And I will show you some of the experimental work we have done in order to understand what kind of microphysical mechanism could link cosmic rays and clouds. And then I will talk about whether this microphysical mechanism is something that you actually can see existing in the real atmosphere. And I will talk about it on two different timescales. One is on very short timescales, and one is over the last 60 years. Let me see, how does that work? So cosmic rays are, as we just heard, energetic particles which are accelerated by stellar processes. And the process is a supernova explosion, where you have a shock front that is capable of accelerating particles to enormous energies. So in the interstellar space, you have these particles moving around, and some of them, they will of course hit the region of space which is sort of governed by our star, which is the sun, and this region is what we call the heliosphere. It is such that about half the particles that are outside, it's only half of them that are able to penetrate to the distance of the Earth. So the solar activity actually acts as a shield against cosmic rays. And if we have a change in the solar activity, then it modulates the amount of cosmic rays that can enter to the system. So this solar modulation gives you a variation of the order of 10%. It's on that size. But what happens when these particles enter to the atmosphere? Well, here you see an animation of, this is actually Chicago and one of the Great Lakes. And we go up in about 20 kilometers, and we have a particle, it's a proton coming in, and you see this shower structure that evolves down through the atmosphere. So you have one particle coming in, and it, in this case, becomes millions and even billions of other particles. And these particles, they interact, of course, with the atmosphere. It changes the chemistry in the atmosphere because you have all these ions. So, and ions are important for chemistry, but it also produces cosmogenic isotopes. So one of the cosmogenic isotopes is carbon-14, which you know very well. And this is very fortunate because this carbon-14, it might go into the tree rings. And by measuring how much carbon-14 there is in a certain tree ring compared to carbon-12, it says something about how active the sun has been at that time. So these cosmic rays are entering into our atmosphere all the time. You can see down in the bottom here that about 70 muons is going through each square meter per second. And so these particles, it sounds exotic, but they are actually a part of life, and they have always been. So the question is, then we have these particles, and I said that there were empirical evidence that when we have a change in cosmic rays, we also have a change in climate. So here I'm showing you one example, but there are so many examples from all over the world where you see these correlations. And what you are seeing here is actually from stalagmites, so it's from a cave in Oman, and you cut out one of these and you make some studies of it, and you look for instance, for oxygen 18, and you get this blue curve, and it's from 6,500 years ago until 9,500 years ago. And you see this variation that you have, and that's simply, I mean, it's believed that it's because the monsoon over this cave in Oman is changing, and it's changed the amount of rainwater that comes to the cave, and you get this time variation. But if you look at the top, that is the change in carbon-12 over, of carbon-14 over the same period. And this is a global signal, but you see there's a remarkable correlation between the two. And the carbon-14 is produced by cosmic rays. And in the bottom here, you see a amplification of the axis, so it's 400 years, and you see even on this time scale a very nice correlation between the two. So another thing which we just discussed was a little ice age. This is the last 1,000 years. We have the medieval warm period, we have the little ice age, and I mean there's no doubt that this period, the little ice age, was a hard period for people in Europe. There are many reports about people starving and so on. So it was really bad times, and you never had. I mean, in the little medieval warm period, you didn't have periods where you had frost in the months of May, for instance. That was very, very rare, and I don't think there's any records of that. But here you had that the crops were destroyed by this bad weather. But if I compare this with solar activity over this period, and this is again the carbon-14, and it is of course a product of the cosmic rays entering into the atmosphere. And the axis is actually going down, so here you have low solar activity, so you have many cosmic rays. Here you have high solar activity, so you have fewer cosmic rays because the screen is stronger. But you see that there is this very nice correlation. So there is something to understand, and I think it's important also to mention, and this is what we just talked about, that solar irradiance seems to be too small to explain it. The variations are small, at least this is what is commonly accepted at present. So some kind of amplification mechanism is needed. So that is really where my work started. And that was the speculation of what could an amplification mechanism be. And the idea was very simple, that it could be that clouds are changing because of these. I mean, if cosmic rays are changing, maybe it can change the amount of clouds that you have on the Earth. And if you change the amount of clouds, of course, you change the amount of energy that reaches the surface. So it would be a very effective way of doing an amplification. And I should say that the net effect of clouds, it's about, the net effect of the forcing is about 30 watts per square meter of that order. It's of course two effects. You both have a heating and a cooling effect, but the reflection of light, sunlight, out into the atmosphere, out into space again, is the dominating effect. So when you had this idea, what we did was to take satellite data of clouds and compare them to the cosmic ray changes. So this is from 1983 until 2006. The red curve is changes in the cosmic rays as measured by a neutron monitor. And the blue curve is low clouds from the ESCIP data set. And I should say that, I mean, first of all, you see there's a nice correlation. There are problems with the calibration of this data set, so we did a recalibration over this period, and that is controversial. But in any case, this correlation does not say that there's a causal effect. I mean, it need not to be cosmic rays that are causing this change. It could be by accident that there is such a correlation, or it could be a correlation with another part of solar activity. Okay? So, but when we showed this type of figure, people were saying that that there's no known mechanism. But I want to show you now that we actually can through our experiments, find a very nice relation. But let me just summarize that there are this empirical evidence for a relation between cosmic rays and climate. And it opens this question, which I will try to give you an answer to. If there is a link between cosmic rays and clouds, what would the mechanism be? And in order to answer that, we have to think about how clouds are formed. And it turns out in order to get I mean, most of the clouds I'm talking about are warm clouds, meaning that they are liquid clouds. So they consist mainly of water droplets, but in order for the water vapor to condense, you need a small particle in the atmosphere, and this is an aerosol. It's a small cluster of molecules that are floating in the air. It can be liquid, it can be solid. Now, the interesting part is that it is known that many of these aerosols, they are actually formed directly in the atmosphere from trace gases. So you have a conversion from a gas phase to a small liquid phase or solid phase directly in the atmosphere. And the question is, how is these small particles actually stabilized so they don't evaporate again? And it turns out that this nucleation process is not really well understood at present. And our idea was to look at the role of ions, the ions produced by cosmic rays. So you have cosmic rays coming in, and the idea is that the ions somehow help stabilizing these small clusters that then subsequently can grow to a size where they become what we call cloud condensation nuclei. They have to be of a certain size, otherwise they will not seed these cloud particles. So the idea is that by turning up and down the amount of cosmic rays, we should produce more or less of these small particles. And this is an experimental question that we can try to answer. And we did that at some point a number of years ago in our first experiment where we had a reaction chamber. It was about 8 cubic meters. And the idea was to take in these trace gases, sulfur dioxide, ozone, and water vapor. And then the difficult part is to have these trace gases in atmospheric concentrations. But then you put everything inside, and the only thing you vary is the amount of ionization in the chamber. So the idea is by changing the ionization, you will then look to see if you produce more aerosols. And it turns out that in our experiment, we actually see this effect. You see here the increase of the ionization in the chamber, and up here you have the production of small particles. And you see, as we increase the ionization, we actually increase the number of small particles. And we have repeated this type of experiments many times, and we still see the same type of behavior. And just to show you one of the other experiments that we have been doing, this is actually done in the UK. It's done in the Bulby underground laboratory. And the reason is that we want to get rid of cosmic rays, so we could make some experiments where we knew that ions were not playing a part of the nucleation. But I'm not showing any results. This is actually the chamber. And you see all the screening here. This is actually solid copper, and this is lead in this experiment. So we did this experiment, and it seems as if there is a microphysical mechanism that is producing more small aerosols. So the standard response to this, and was also what Mike Lockwood was saying, that there's always plenty of CCNs in the atmosphere, that is cloud condensation nuclei. So this mechanism that we have with our small, that we show with our experiment, will not be important because these particles, they will just drown in all the other processes that are going on at the same time. So it is probably not important. But I think we actually can answer this question directly. And what you see here is actually the solar activity. We have a screen, so you don't see the direct light from the sun, but it is sort of the solar atmosphere. And you see it's a very, there's large variations in the solar wind, and these are what we call coronal mass ejections. And if these coronal mass ejections get close to the Earth, because they are sort of a magnetic plasma, they actually screen against cosmic rays. One of the largest events was actually in 2003 at Halloween. What you have here is the sun, and you have the Earth at this point here. And then you see these two sort of plasma clouds that are moving out through the interplanetary space. And when they cover the Earth or get close to the Earth, you actually see this drop in cosmic rays. Here is one of these examples. And when you measure them at Earth, they are actually called Forbush decreases, after the man who first discovered them. And what you see here is within hours, you actually have a big drop in the cosmic rays on the order of here 15 to 20%. So you can, within hours, have a drop that is equivalent to what you have over a solar cycle. So you can say that these events are like natural experiments of the sun with the whole Earth. And we can now see if we can find any response in the Earth's atmosphere over this. And this is, I should say that we found about 26 events over from 83 until present that were of a certain size that we found significant. So there are many small events, but we are looking at the larger events, and we used a lot of effort in order to understand which events were strong and which were weaker. So we could rank the events. But what I'm showing you here is mainly for the 5 strongest events that I add together in order to get a good signal. And this is the problem you always have in this game, that there's so much natural noise or variability in the system. But what you see here is day 0, when this plasma cloud is passing very close to the Earth. You have a minimum in the cosmic rays. And then we go 15 days earlier, so then you get the minimum. Then about 20 days later, this plasma cloud has moved out, and the cosmic rays are more or less going back. And then we look at this data set, which is the SSMI. It's a microwave imager, and it measures actually the liquid water in the clouds over the oceans. And you actually see here a very significant drop following these events. Now, in order to investigate whether it was just because we are using this satellite data set with one particular algorithm, and they are not, I mean, these clouds, these satellite systems, I have another here which is Moody's, they are not up at the same time. They are covering different time periods. But we see the same effect in all the other data sets. Like here, this is the ISKIP data set. And I should say that this drop here is actually on the order of 6% in the liquid water content. It's a huge effect. And the change in ionization is only on the order of 10, 12%. So it indicates that this mechanism might be quite important for what is going on. Now, this was all in the cloud properties with satellites observation of the clouds. But I also said that the aerosols were affected because that is the basic idea. And here we have this data set which we call the AeroNet. It's actually observation from the ground, where you look at the sun and you actually look at the color of the sun, because it says something about how many aerosols there are in the air. And you actually see very clearly a drop in the aerosols. So you have actually fewer small aerosols during these events. And I should also say that this is 5 events. I mean, if I take out one of these events and I add the other 4, and it doesn't matter which I take out, I still get the same signal, more or less. So it seems very, very robust. So something is going on. Yes, I'll just take the... So the idea is that we have these cosmic rays coming in here, and then in order to affect clouds, they have to have a certain size, which is on the order of 0.1 micrometer. So the idea is that we have a generation all of a sudden produced of small aerosols, and then as a function of time, they grow, and it takes a few days before that happens. And that's why there was this delay in the data. At least that's how we interpret this. So it looks as if that from solar activity to cosmic rays ionization, we seem to see the whole chain operate actually on a global scale. So it looks as if on this short time scale, so we have the experiments, and it seems to be operating on the time scales of days to weeks. So the obvious question is, of course, and this is the last part, is whether this effect can also be seen in the climate over the last 60 years. And what I'm using for climate here is actually the ocean heat content from 0 to 700 meters. And what you see is that this is the change in the ocean heat content over this period. You see this very, well, there's a rise in the ocean heat content over this period. Now, I want to do the following, and it's fairly similar to what Mike Lockwood was doing. So I want to do a very simple modeling, and the idea is that the change in the radiative forcing is really what determines how much heat goes into the ocean. So if you have a change in the net forcing, for instance, a positive change, then the heat content of the oceans will rise, and vice versa. And you have this very, very simple model between the two. Now, in order to make progress, you have to make some assumptions about what kinds of forcings that you're using. And I'm also using aerosols, just like Mike Lockwood did. And then I'm using solar activity, and I'm using the cosmic ray variation. And then, surprisingly, or maybe not, I don't know, I will talk about a regime shift that happened in 1977. And then I will also have an anthropogenic forcing. But the surprise is, let me just give you an idea, and this is the same heat content change over this period that I showed you in the beginning, and this is actually the index from volcanoes, and you see that you have a cooling from these volcanoes, and you can actually see the effect here, and you can see the effect here in the data. Now, I can then sort of reconstruct which parts are from solar activity. So let me try to reconstruct that, and I get the following. So down here I have what appears to be the cosmic ray. This is cosmic rays, just with the axis inverted over this period. And what you notice is that the data, this is actually just the slope of these data here. They have this very nice wave pattern following this curve very nicely over this period. But what is surprising is the size of it. The amplitude is on the order of 1 watt. And this amplitude is actually very consistent with the findings of Nir-Shaviv, who used a different model, a more involved model. And he found the solar cycle amplitude to be about 5 to 7 times larger than from solar irradiance alone. But the interesting thing is that if I remove the solar cycle signal or the solar signal from the data and look what is left in the ocean heat content. Sorry, I'll just skip that. No, let me show you that. It was just to show you that if I add the clouds on top of it, you see a very nice correlation over this period. But if I now remove the solar cycle, then I actually left with a very curious step in the heat content, and it happens around 1977. And I can see in the forcing, it's like having an impulse of forcing over this period. And it's well known that something happened in 1977. In the Pacific, you have the Pacific Decadal Oscillation. It was actually observed by, all of a sudden, you couldn't catch salmon in the regions where you usually could catch them. It had big impact on the fishery industry. But it also shows up here very nicely in the ocean heat content. And you can actually also see this effect around 1977 in the tropospheric temperatures. Here you have 1977, and you see sort of a certain level here, and then a big jump up to a different level over this period. I think you can see it very clearly here. So that is the regime shift that happened during this part. So this is my last slide. It certainly looks, I mean, if I now combine all the effects I'm talking about, I get a very nice, this is a black curve, you get a very nice correlation with the ocean heat content. But what I also see is that it looks as if solar activity had a large impact on how this heat content has evolved over this period of time. And it's interesting, I mean, if I ignore the solar activity or the regime shift, then what you would call the anthropogenic effect, it actually increases with a factor of 2 to 5. But if you include the solar activity and the regime shift, then this gray area is actually what you would call it could be an anthropogenic effect in the data. And it is exactly solar activity and this kind of natural variability in the form of regime shift that climate models have great difficulties in modeling. So that might be something that need to be considered. So let me just conclude that it looks as if these particles from space are extremely important for changes in climate. And I haven't even discussed a long time, that is over millions of years, where we on geological timescales find remarkable correlations as well. And the evidence seems to suggest that cosmic rays are linked to climate through clouds. So I think we have an experimentally, we see something that could be the physical link between cosmic rays and clouds, and that has to do with the aerosol formation. We saw in the observations that changes on the order of 6% in liquid water for a 10% change in ionization. It's huge. It's something that needs to be understood. And I also think a large fraction of the increase in the ocean heat content could actually be due to natural causes like solar influence and this regime shift in 1977. Thank you.